So we've done area under a curve, and we've done area between curves. Right now, what we're going to do is we're going to take a curve. So let's say I have this curve right here, and we're going to imagine taking that curve and rotating it 360 degrees around the x-axis. So in this case, it would make sort of like a big bell or a big horn. Okay? And no matter where you decided to slice it, so if I went and I decided to slice it right here, the shape that would be made, because it was rotated perfectly around 360, everywhere that you cut it would make a perfect circle. Okay? And you know how to find the area of a circle, right? It's just pi r squared. So if we think about stuff that we've done before, like figuring out the area of a cylinder is just the circle on the bottom times the height. And I always imagine stacking like circular pieces of paper all the way up that would fill the whole thing, and that's what volume is the space amount to fill the whole thing. Perfect. Now we could do the same thing for this shape. We would just have circles of different sizes as we moved along. Well, how do we calculate those circles? Well, we would need to find each radius on its own, and then could find the area of the circle. Now, each radius on its own, if we think about integral calculus finds the area under the curve. And if we found this blue area under this curve, I want the blue crayon for this. If I found the area under this curve, that area would consist of adding up all of those radiuses in another way of seeing it. And if we use integration to make smaller and smaller rectangles, as those rectangles get smaller and smaller, they basically become a radius. So if you wanted to find the volume of any curve rotated 360 degrees around the x-axis, all you're going to do is you're going to do the integral of pi r squared, where the radius is always the function. Because if I plug in any value of x and solve for y, I get the height, which, after that's rotated around, would be the radius of a circle. So then the volume can be calculated just by exactly the same thing. Finding the entire finding function, squaring it, because the function becomes your radius, and you're basically doing an integral of pi r squared. And similarly, if we wanted to really make a bell and take out the middle section, it's the same thing. You could do the volume of the big one, subtract the volume of the small one, and get the total volume in the end. So this is what we're going to imagine. Oh, we're going to color code things nicely here. We are going to graph x cubed, and from 1, 1 up until 2, 8. And we're going to rotate this about the x-axis. So as far as drawing a picture from this, we're going to learn some skills for drawing rotations around 360. This is art classes coming into play. Whatever distance you did 1, 1, do the same distance for a point down there. And same thing, 2, 8, do the same distance there. And then you're going to draw a circle there, an oval. And an oval there, and repeat the curve back. Now, as far as color coding this, to help visualize it better, I hope you brought your crayons. I like to color the outside, so this part here I'm going to color in green, in one color. And then I like to color the cut section. Oh, this is like a watermelon. Better to think of watermelon than to think of blood. So I just cut something. Yeah, so then does that help you see the shape a little bit more? The round part where it was cut, if you turned it, that would be a perfect circle, that red part. And then you'd have another perfect circle here, but you can't see it because of the way 3D objects work. That's why I just sort of drew a dotted line with that circle in the background. And if you had a watermelon of this shape, we want to find its volume. So the volume will equal the integral from 1 to 2. Now you can put the pi inside or the pi outside, because it's one of our properties of integrals. If you're multiplying by a constant, that constant can be brought out in front, or you can keep it inside. We'll bring it out just to make life a little bit easier. And then our function was x cubed. That's our radius, so it needs to get squared, dx. And we get the integral of 1 to 2 of x to the 6 dx. Reminder for definite integrals. We calculate the integral, just kind of add 1 to the exponent and divide. Put it in square brackets. And then plug in one number and subtract the other number. So 2 to the 7 is 128 over 7. And 1 to the 7 is 1 over 7. So its volume, whatever units that would be units cubed. Its volume would be 127 pi over 7. Which again, the person who came up with this idea that, oh, if integration is just the area, and those areas are little rectangles that are getting smaller and smaller, those areas will eventually become radiuses. And if we can calculate volume as just a bunch of circles added up, we can use those different areas and then just rotate it and make a volume. Because before this, to find that volume of any crazy shape would be like, oh, that's too difficult or hard to imagine. So again, we're going to draw this one. One of the things that's going to be helpful is if you can remember how to graph certain things from grade 12. So here we have a square root graph. We know the shape of a square root graph. It's been translated 1 to the right. So it's going to go like this. We have the point 0, 1, and we would have the point 5, 2. So again, equal distance down, reflect it over draw an oval for a circle on that end. What should we make? Oh, this time I know what I'm going to make. Going with the red theme on the inside. So either we could think of this as like, with the orange, I kind of think of it looks like a big ham. Could be a football, but I don't know what would be inside the red air that was inside the football prior. So we've got this shape, and we want to find its volume. So again, the volume is just the area of a circle with an integral pi from 1 to 5 of our function, which was x minus 1, but then that gets squared. Oh, life is so nice. Because this works out beautifully once you square it. To just x minus 1. So I don't know if you noticed that when I'm setting up my notation, I sort of set things up with my brackets ahead of time just to make sure that I don't start to do calculations too quickly and then lose track of where things are. So this pi is out in front, so I put a big set of square brackets. Now I can plug in the 5, 25 over 2 minus 5. And I can plug in the 1, 1 over 2 minus 1. If I do a little bit of the math here, 25 over 2 minus 1 over 2 will be 24 over 2, which is 12. I'll still have the minus 5, but then I have a plus 1. And its volume is 8 pi. Are you okay with the 12 that I put the 25 over 2 and the 1 minus 1 over 2 together to get 24 over 2? Then I was dealing only in whole numbers, which I thought, oh, that's kind of nice. Okay, now we are going to imagine area between curves and find the volume of the following shape. This one, again, you almost do have to be somewhat of an artist to draw it to be able to picture what's happening. Okay, what we're going to have is you're going to find the volume with the region between sine x and cos x. So this is, first of all, an area question where you're subtracting, and then you're going to find the volume of both of those shapes when you're subtracting. So, as a starting point, we're going to draw a picture. A cos graph starts at 1 and goes to pi over 2 is where it would go to 0, and then it would keep going like this. So there's one full revolution up to 2 pi of what your cos graph looks like. Draw that one in black. Then our sine graph starts at 0, then it would go to pi over 2, and then it would keep on going for one full revolution. And it just so happens that right here, where they intersect, happens to be at pi over 4. So what we're going to imagine is that the area between these two curves, which I've highlighted in brown, that gets rotated 360 degrees. Okay? So, how do we rotate something 360 degrees? Well, this point up here, I'm going to measure that exactly down the same other side there. The blue point at pi over 4, I'm going to measure that distance and draw that point there. I'm going to redraw my black curve, would go to that point like this, and my green curve, I'm going to just draw it the dotted line like that. Now, I'm going to take the blue points and draw an oval. And I'm going to take the black points and draw an oval, but this part you wouldn't see. And what it's going to make, you can visualize this, what it's going to make is it's going to sort of make a dish or a bowl, okay, on its side. Because the part that's cut out would be like the inside of the bowl. And so I'm going to paint the outside of my bowl with brown crayon. So here is the outside of my bowl, and the inside of my bowl I'm going to color in purple. Now, this is actually hollow, not a perfect section this time, right? Can you see that or visualize that? So now we've got a dish, and the purple part would actually be hollow all the way into there. Maybe I'll shade a little bit of purple on the inside. So we've got a dish. If I take away, or maybe is it better if nothing's colored to make it empty like that? Can you visualize that better? So now we need to find out how much volume it would take to make this dish. Right? Maybe you're 3D printing it and need to know how many little pebbles of plastic you have to stick into the machine in order to make this work. So in black, if I wanted to find the volume, if I just did the black part solid, that would be, so my total volume will be the volume of the black part, which goes from 0 to pi over 4, and that would be cos squared, because that cos would be our radius. Then we need to subtract the volume of the green part. I'll do the sine part in green. It's also from 0 to pi over 4, and that would be sine squared x dx. And we run into a little bit of a problem. The problem that we run into is if I try to do the integral of cos squared, that's a chain rule, because cos is inside of sine. But unfortunately, I can't use integration by substitution, because the derivative of cos is just sine, and that doesn't appear. And also we run into a problem, because I can't use integration by parts, because there's no other part other than the cos. So, what do? We can, in this case, factor out the pi out of the whole thing, because there's a pi in common in both of them. And then when you have an integral minus an integral, you could put them together as just one integral. And initially, it might feel that this wasn't helpful, because if you couldn't do the integral of cos squared by itself, and you couldn't do the integral of sine squared by itself, putting them together still means you'd have to do the integrals by themselves. However, if you recognize that this is an identity, that cos squared minus sine squared was one of the identities we learned in our trig identities unit, we can change this to cos 2x. And that is an integral we can do. So, integrated integral will be sine 2x with a chain rule, have to divide by 2. pi plate. If you plug in pi over 4, you get sine of pi over 2. You remember what sine of pi over 2 was? Y coordinate? 1. And if you plug in 0, sine of 0 is 0. And you get pi over 2 as your answer.